So thank you very much for introducing me. I gave this talk last week in some version, so I apologize for those who've heard it already, but maybe I will try to emphasize something else today. Maybe I just move this off. So my plan is to do these 12 things. I will give you the geometric setting of pre-target theories. I will define the geometric recursion for any target theory. Then I will give you the detailed definition of target theory, and then a remark of why the recursion is well defined. So I think I wanted to give this audience the precise definition so you can see the analysis that goes in. Then I will give you an example of Teichmüller theory as a target theory. I will show you that it fits perfectly with the work of Mirzakhani and McShane. I will then show you that if you tropicalize those initial data, you get actually Conservatis's example, which computes all the pairings of the psi classes on the moduli space. I will then show you an example of sums over multi-curves and how that fits with geometric recursion. And I'll just briefly discuss the relation between topological and geometric recursion for the case where the target is Teichmüller theory. And then I will just give you a little cute example from closed string field theory that it actually fits, namely what's called a topological vertex fits very well with geometric recursion. And then I will show you open geometric recursion, and I will show you how that actually leads to a recursion for statistics of eigenvalues of the directly ordered Neumann, the Plas-Beltrami operator on a compact surface with corners. Okay, so let's get started. So first we do a little bit of a watered down setup because it's easier to get some idea. So I will take at first go the category of compact oriented surfaces. So they're allowed to have boundary, right? But it's a smooth boundary. If they have boundary components, they are smooth. And morphism, they are isotopy classes of diffeomorphisms. So actually this category is a groupoid, right? All morphisms are invertible. And then I take as the target category, I take the category of vector spaces. And I am interested in a situation where I have a functor from surfaces to vector spaces. And such a thing I will just call a pre-target theory. So in other words, to any compact oriented surface, it associates naturally a vector space in such a way that, diffeomorphisms act on these things. And so in particular, I get a representation of the mapping class group on each vector space associated to each surface. Okay. And now what I am really interested in the context of geometric recursion is some kind of functorial assignment of a vector inside the vector space of any surface for all compact oriented surfaces. And I want it to be a functorial assignment, so of course this means that it will be mapping class group invariant vectors that one assigns to every surface. Very good. So there are indeed many constructions in geometry and topology which involve surfaces that really fits this framework. Normally I give a whole stack of examples. I will only give you 4 examples here today because I only will do something that's related to these. And now all these 4 examples are only for Teichmüller theory. So therefore you could very well be led to believe that geometric recursion only has something to do with Teichmüller theory, right? That is completely wrong. Geometric recursion is about many other target theories than Teichmüller theory. But I give you 4 examples that involve Teichmüller theory now. The first one is that I take the Teichmüller space of the surface, and what I mean by that is simply just the Teichmüller space of hyperbolic metrics on the surface in such a way that boundary components are geodesics. Okay? So that's the Teichmüller space. Then I take continuous functions on Teichmüller space, and that's the vector space I associate to a surface. And the vector that I want is the function 1 inside, as a function on Teichmüller space, and that's of course mapping class group invariant. So this is the simplest example one can almost think of. It's not exactly the simplest example you can think of, but it's the simplest interesting example, it turns out. Funnily enough, you may think this is utterly uninteresting, right? Associate the function 1 on Teichmüller space. But the thing is, we will actually construct this using geometric recursion. And this will use Mirzakhani's generalization of McShane identity. Renat?
The examples with finite dimensional.
Yes. So associate the complex numbers to every surface, and associate 1 in the complex numbers to every surface. Yeah, that. Well, funny you are still smiling, but of course that's utterly uninteresting, right? But there are actually some in relation to TQFT. Okay, so if there are reducible TQFTs, you can get something in the endomorphism space that's mapping class group invariant, and that's another application of this potentially. Okay, I want to show you a second example, more interesting. The vector space, so the functor up here that I'm talking about, is exactly the same as in this example. It's still continuous functions on this Teichmüller space, but now I consider a discrete set, the set of multicurves on the surface in the way that Thurston defined it and used that word. So that is the set of isotopy classes of embeddings of closed one-dimensional manifolds inside the surface, such that no component is isotopic to a boundary component, nor are any two different components isotopic. And so when you have such a guy, it has a number of components, right? So I sum over all possible multicurves, I take a product over the components of the multicurve, and then I apply some function f to the length of the component. And so this becomes now a function on Teichmüller space because it depends on this point sigma in Teichmüller space, and f is just some rapidly decaying function at infinity. So for example, if you take e to the minus s times x, that's fine. That's certainly rapidly enough for all topologies, actually. Okay. So let's do exactly the same target again. So I look at continuous functions, but now I do something more serious. I take namely the Dirichlet or the Neumann, the Place-Beltrami operator on the Riemann surface sigma here, or the hyperbolic surface, and then I apply f to it, where f is again sufficiently fast decaying at infinity, and then I take the trace. And so that's another function that is continuous mapping class group invariant. Okay. And I do not believe that that guy satisfies geometric recursion. So that's an example where I don't think it satisfies geometric recursion. I cannot exclude it completely. Okay? I will show you, what I will show you is that open geometric recursion actually can deal with this guy. And so that's a motivation for open geometric recursion. Okay, last example is just to show you that the target theory does not always have to be continuous functions in Teichmüller space. So if you skip right down here, the target theory will now be all forms on Teichmüller space. And what I will do is, if I look at the Teichmüller space of a surface with a boundary, right, I can somehow foliate that by Teichmüller spaces where I fix the length of the boundaries. So that just foliates the space here. And what I can do is I can now construct a Weil-Petersen symplectic form. It's a 2 form on this Teichmüller space where I have fixed the length of the boundaries. And what it is that, well, a nice way to write it is to choose a pair pans decomposition of the surface. That gives you French and Nielsen coordinates on the surface. So that the first coordinates are the length of the curves, and the second coordinates are the twist parameters with respect to these curves. And so if you just define this standard symplectic form in these coordinates, then actually that turns out to be mapping class group invariant and a well-defined global symplectic form on this Teichmüller space here where you fix the length. So actually when you don't fix the length, this is a Poisson manifold, and its symplectic leaves are exactly when you fix the length of the boundaries. And then what the form I take is simply the exponential applied to this symplectic form. So that means with respect to wedge, so it starts by the function 1 plus omega wedge squared plus omega cubed wedged, and so on. And so the top form will be the usual Liouville form on Teichmüller space. That's another mapping class group invariant guy. Okay, so now I want to specify precisely which target category, which category of surfaces I actually want to consider at first. So I want to consider compact-oriented surfaces, as I said before, but I will only consider those that have negative Euler characteristic. And now I'm asking that there is a mark point on each boundary component. And I also asked that there is an orientation on the boundary in such a way that the boundary is split in the ins and the outs, depending on whether the orientation agree with the induced and the given one, or they disagree. And then I am looking at the inclusion of the in boundaries into the whole surface, and I want that to induce an isomorphism of pi zeros. This simply just means that every connected component of my surface has exactly one in boundary, all the rest out. So there's one specified in boundary, all the rest is out on each component. Okay, and morphisms are isotopic classes of orientation preserving diffeomorphisms, which preserves the marked points and orientations on the boundaries, modulo isotopies that also preserve all of that. In particular, a Dean twist in a curve that's parallel to the boundary will act non-trivially here. It will be considered to be a non-trivial element in the mapping class group. Okay, now at first go, the category of vector spaces I will be working with is Hausdorff complete locally convex vector spaces over C. So these are the vector spaces whose topology is given by seminorms, but it may be an uncountable amount of seminorms. That's allowed here. Examples of these are Fresher spaces, and you notice I gave you Fresher spaces before. In fact, some of them were Banach spaces. But that's also examples. And then morphisms are just the standard morphisms of locally convex topological vector spaces. And so a pre-target theory is simply a functor from this kind of surfaces here to this kind of vector spaces here. Good. And so here in this one slide is the whole idea behind geometric recursion and its setup. So we suppose up at the top here that you're given a pre-target theory, so that means a functor from S to C. We now want to recursively define a vector that is mapping class group invariant at each of these vector spaces. We will recurse on the Euler characteristic. The basic idea is to remove pair pants that are embedded around the in boundary. So for each connected component we do a construction one at a time. We embed a pair pants near the in boundary. Let's say this is the in boundary, this is the in, and this is the in. And then we remove the pair pants and consider the complement. That will be called sigma C. And then the point is, when we take out this pair of pants, no matter how it is embedded, the Euler characteristic will go up by 1. And since I'm only considering negative Euler characteristic surfaces, it will end at Euler characteristic equal to -1. And there are two cases left, a pair of pants or a one-hole torus. So therefore, if I want this whole thing to run, well, I have my pre-target theory. But I now want it to be a target theory. And being a target theory means two more things. It means that I have disjoint union morphisms, which are bilinear maps like this. And then I have gluing morphisms, which are also bilinear maps like this, where this is the surface that is obtained by gluing sigma 1 to sigma 2 along a disjoint set of pairs of boundary components, outs from the first and ins on the second. So if I have this, I can I can run an iterative process, because I imagine that I have something that I want to have in these pair pants. I have iteratively already defined the vector for the complement, and then I use the sewing and disjoint union morphisms to build the vectors I need. So therefore, starting data, well, that was this pair of pants and the one-hole torus that I must have. So I must have an A inside the E mapping class group invariant part of the pair pants. Same thing for D. And of course, then I just assign those two to be the vectors for the pair pants and the one-hole torus. And now I need also recursion data. So I need something to put in the vector space for the pair of pants of this type and of this type. So I didn't discuss what these types are in difference yet, but you see up here the embedded pair of pants has two boundary components in common with the surface, and here it only has one. So that's the difference between B and the C case. The C case actually splits in two, namely where the complement is connected and where the complement is disconnected. I could have chosen two different C's for whether the complement is connected or disconnected. But in order to line up well with topological recursion, I won't do that. So I'll just choose one and the same C for these two cases. Okay, and now, so what I want to do now is simply just, if you were thinking TQ of T, you would just say, I just take one vector for this, one vector for the pair of pants, and I glue them together and I get the vector for the whole surface. But this is not TQ of T. So quantum field theory has this locality property, right? That if you split the space in two and you have somehow the state for one side and the state for the other, you can have a sort of inner product that gives you the glued thing. And so that's locality in quantum field theory. But in string theory, you don't have locality. You have somehow worldsheet diffeomorphism invariance. And so that's really what we want to build here. So we really want to build something that is mapping class group invariant. And that means that we're actually forced to sum over all ways of embedding these pair pants up to isotopy. And therefore, we end up at the following iterative formula that omega sigma is simply the sum over all possible ways of embedding a pair pants of this type up to isotopy. You apply the gluing map where you stick in the recursion kernel with respect to B here, and then you stick in what you have already glued for the complement. And then you use the gluing morphism, you get an element in E of the vector space for the glued surface, and then you sum. Same over here. Now, one little snack here is that there is an upper B here on this B. And that's because a pair of pants has one in and two outs. And therefore, when I'm taking this pair of pants and I embed it in this surface, well, clearly the in has to go to the in. There's no choice there. But then when I look at the pair of pants, there are two outs, and I can decide which of the two outs goes to the boundary of the surface I'm embedding it in. And so that's what this little up B means. It's a selection of one of the boundary components that has to go to the boundary of the big surface. So there are actually two B's, right? One for the right leg and one for the left leg of the pair of pants.
This is the one that's colored red?
The non-B is covered red here.
The non-B, right.
So this guy here this is B1 and this is BI, so this is B1, BI. So this notation here is copied from an old version of our paper, so don't agree quite with the notation I have here, sorry.
But it's the n of omega sigma C.
Yeah, that would go to the opposite boundary. So, if I say that my head goes to one boundary, my left leg here goes to the other boundary, then the red is the right leg.
All right.
That goes there.
All right, got it.
Yeah.
Are the left and right related? Or the other way?
Yeah, I will show you that on the next slide.
So
That's right.
B belongs to E or
A pair of pants. Yeah, just like C does.
Oh, yeah.
So this belongs to, goes for both of them. Okay, very good. So indeed, as Ralph just pointed out, so let me recall, what is initial data for us? It's A and C that lies in this space, the E for the pair of pants, mapping class group invariant part. And then I have two B's, right? Two of them, but they are related in such a way that if I have a diffeo of the pair of pants that switches the two legs, then it must intertwine the two. Okay. And that, of course, I want mapping class group invariant, so I have to be able to switch them. Very good. And D is just an element in the one-hole torus guy, mapping class group invariant. And then there is some decay properties that these things satisfy. I will get back to them in a second. And if they satisfy these decay properties, then there is a theorem here that says this works. This gives you, this assignment is well defined, and it gives you, in fact, absolutely convergent series in the seminorms for this vector space.
Oh, sorry, the decay properties apply to what?
Yeah, so there are some decay properties that A, B, C, D has to satisfy.
the decay with respect to what?
Yeah, some norms. I will show you what that decay properties are actually right now. But I just want to state that under certain decay properties of these guys, it's actually B and C that has to satisfy them. Decay properties A and D are no constraints whatsoever. Then you will get these sums of actually that they converge absolutely. So it's just this says exactly what we've just discussed, except maybe that what I didn't say before was that if a surface is not connected, you just use the disjoint union morphism to define it to be just the morphisms of the connected pieces. Okay, so let me now tell you why this theorem is true. And what are these decay properties that have to be satisfied? So unfortunately, I have been lying so far about the true target theory. Because the true target theory is more complicated than what I've been telling you so far. And that's because we can't prove the convergence if the target theory is only just a single complete convex locally convex Hausdorff space. You have, so here is the true category that you have to consider. So the true category is a directed set. So a directed set is a pre-ordered set with the domination property. That means that any two elements, there is a third that's bigger than two of those. That's a directed set. So you have some directed set.
Does it come from the category S somehow?
No. The way you should think of this I here, so that you can have some understanding what's going on here, is that think of I as the positive real numbers. And then think of the Teichmüller example. And of course you can take continuous functions on all of Teichmüller space. But what you really need to work with are actually continuous functions on the system sets. And so that means you take the subset of Teichmüller space for which the shortest geodesic is bigger than epsilon, where epsilon runs to this R plus, and then you get this directed system of these vector spaces. And that's the kind of thing one has to work with to get the analysis going in that example. And that's why we introduce these guys like this. Okay, so we have a directed set, and then we have complete Hausdorff locally convex vector spaces indexed by that set. And then of course they come with their set of seminorms. This is AI. That's what I've written here. So the seminorms are indexed by two things, one from the indexing set I and another from the set that indexes the seminorms for that I. So the seminorms have two indices. Okay, now the category of complete Hausdorff locally convex topological vector spaces have projective limits. So when you have a directed set like this, you automatically get a projective limit of this. In the Teichmüller case, that is all the continuous functions on Teichmüller space. If you take all the continuous functions on the system sets, then system sets expand, or exhaust the whole space. So that's all of them. But then I look at a subspace inside the projective limits, which I call V prime, and that's the guy for which all these norms are finite. And what are these norms? These norms are the for each I, you just take the supremum over all seminorms of the seminorms here, right?
But not uniformly, necessarily.
Not uniform in I, but uniform in all the seminorms for that vector space.
Right.
And so these vector spaces, of course, have the property that this supremum will not be finite for a general element, but I look at the subspace for which this is finite. Okay, so what does that mean in the Teichmüller case? Well, so this V prime here is exactly, first of all, what is this norm for Teichmüller space? So I here would be an epsilon, and this is simply just the supremum norm or the function restricted to the system set for epsilon, where I is epsilon. Okay, so of course, if there are just continuous functions on that subset, they may not have a finite norm, but there will be a subset that does have a finite norm.
Right.
And then I look at the guys here, which have all of those finite. So these are the continuous functions on Teichmüller space with the property when they're restricted to an epsilon system set, they're bounded on that. But it's they could still blow up right at the boundary.
So your definition is that existence of V prime is the requirement, or?
And no, this is the definition of V prime.
Okay.
V prime could be zero. I mean, but then we will get a very trivial theory because our vectors will lie in V prime.
The V prime doesn't necessarily have a norm.
No, that's right. A V prime is a new vector space of the same type.
Right.
Okay. So, I mean, in fact, V is just all we care about is that V prime is the subspace which satisfies this. Okay. All right. Now, what are morphisms between such objects? Well, they are linear maps indexed by pairs. So, one has maybe I as its directed set, maybe 2 has J as its directed set. So therefore, it's linear maps for V1I to V2J for all I in I1, but then only for all j less than some h of I, where h is an order-preserving map from the ordered set I1 to the ordered set I2, and this should this will induce continuous linear maps between the two projective limits, and we want that this map, that resulting map here, has to take this preferred subspace of 1, 2, 2, and that's a condition. So, sorry, it gets a little technical, but I want to show you how these things really work with this analysis. Okay, so now, what is a true target theory? Well, a true target theory, so category C is this Hausdorff complete locally convex topological vector spaces. So, it is a functor, sorry, that's totally wrong. C is this category here that I just introduced. I'm sorry. So, now a target theory, a C-value target theory is a function from S to this category I just defined. So in other words, the functor spits out for every surface this directed set, and it indexes all of these vector spaces with all these seminorms indexed by these sets here. On top of that, we also want length functions, completely abstract length functions. Don't think hyperbolic geometry. I mean, you can if you want, but you don't need to. Just completely abstract length functions. They are going to be indexed by I, so elements from the directed set, and then alphas from the set of seminorms for that I. It's really funny, but that's actually what you should do. And then the lengths take values in complex numbers. It cannot return 0 on any of them. And remember, this is first on multicurves. So, why? Let's just discuss Teichmüller case, because if I discuss Teichmüller case runningly, you will see the rationale for this. So I didn't discuss actually in Teichmüller case what is this.
Right.
Well, this is just all the compact subsets of the system sets. So first you fix an epsilon, it gives you a system set, and then you take a compact inside that subset. That is an alpha. And then, of course, when you have such compact subsets, you can take the maximum, the supremum of the length function for a curve and for a multicurve on that compact subset. So those are the length functions in Teichmüller theory. Okay. But in general, you just say, I have this abstract gadget here, such that 3 actions have to be satisfied. Here's the first one. And so that's, of course, also inspired by hyperbolic geometry. It namely says the polynomial growth action. It says for any I and for any alpha in the set of seminorms on the ith space, and for all capital L positive real, you consider the following set. You look at all the multicurves that for that seminorm has length in absolute value, because it's in C, so I'm taking absolute values, less than L. That's a subset of S sigma. You want this to be finite, and you want its size to not grow faster than a polynomial that only depends, its coefficients only depends on I. And here you're taking supremum over all seminorms for the given I. That's the polynomial growth action. So this is just in Teichmüller theory saying that if you look at the system set, you get this condition here. In fact, you get this on all over Teichmüller space. Okay. Very good. Now, then I also want a lower bound axiom, and that is saying for any I, there should exist an epsilon I bigger than 0, such that if I, for that I, look at the infimum, where I take infimum over all the seminorms and all the multicurves, and I compute the length, this must be bounded by below by epsilon I. This is the perfect analog of system set. It's saying this: the length of the shortest geodesics is at least epsilon, and it's just so it's a map from I to the positive real numbers, right? So this is the analog of the system set. Okay, and then there's the last one, and that has to do with small pair of hands, and so it says that for all I, there must exist a qi bigger than 0, such that for all the seminorms, if I look at pair pants, for which I know that the length of the interior boundary of the pair of hands is smaller than the outer parts of the pair of hands. So some parts of the boundary is embedded on the boundary of the surface, and some are interior, right? This thing here should be a finite set, and its number should be bounded by some qi that doesn't depend on alpha. Okay, maybe I should speed up because I see that, yeah, it's not easy to take in this definition.
I have several questions, but let's postpone them.
Okay. But yeah, once you get used to these three axioms here, they work really well. They are tailored exactly to work for this theory. Okay. And actually, I think they will be satisfied by a lot of target theories. Okay. So, and certainly hyperbolic geometry is one, but not the only one. All right, now, so the union morphism we've discussed before, I just spell out in detail what I want. I also want it to be associative with respect to the associativity of Cartesian products and associative with respect to unions.
But may I ask a very short question?
Yes?
Why do you, because it looks like it's totally topological, why do you need hyperbolic geometry?
I don't. That's the whole point about this. I just gave hyperbolic geometry as an example to show you, to give you some intuition of why these axioms are like this. These length functions are not necessarily the hyperbolic length. It could be the combinatorial length. It could be one that I decide by some crazy means. It could be higher Teichmüller theory. It could be something I could invent for Higgs bundles, or I don't know what. The length you measure with your, I mean, just think about,
Mapping class group.
there is mapping class group action on everything.
We need some properties with respect to it, or maybe.
Yes, but it's inherent. The mapping class group acts here, but there's no requirement on this being invariant, which, for example, you don't get if you take a hyperbolic surface and you take one curve and you act by the mapping class group. This will have very different length. Right?
But the vectors you choose will be invariant.
They will be invariant under the action of the mapping class group. That's right.
That's the point.
That's very important. And that's the whole purpose of this, in some sense, is to build these invariant vectors.
Right.
But these lengths, that's sort of the whole point about this, is to say we can do something that is much more general than hyperbolic lengths. You're not constrained to have Teichmüller space as your only target theory. No, by no means. For example, all of these axioms here, the polynomial growth axiom and these two axioms here, are satisfied for Hitchin's higher components. So if you look at SLNR and you look at the spectral radius of the polynomial along a simple closed curve, then that guy satisfied all those three.
Would you comment what you get if you apply geometric recursion on that context?
Functions on Hitchin's higher Teichmüller component.
Ah, okay.
Yeah.
And then?
And well, then you should combine it with the new Mirzakhani identity by Laborie and McShane, and more things. That's not, I will mention this on one slide a little later. We're going a little slow here, but okay. So yeah, so we need union axioms and gluing axioms, right? We need morphisms like this and morphisms like that. But this I think you already understood, so that we don't need to discuss that anymore. There are details about what kind of associativity they have to satisfy and so on, but that's not so important. Okay, so now initial data, as before, A, C, B, and D. And here is the precise condition that this initial data has to satisfy. A and D you can choose as you like, as long as you choose them in the prime spaces. No constraints on anything there. But they have to be in that space because I want that the recursion persistently produces something actually in this prime space. And it has to do with the norm estimates I need on the way. What's the decay action? Well, first of all, note the definition of this. This is the function that's 0 for negative x and the identity for positive x. So the positive part. So it says for any connected surface and for any pair of pans that's embedded in this surface, well, then you look at the indexing set for P and the indexing set for the complement of the pair of pans in the surface. You pick I and J there. Then you pick a K in the indexing set for the glued up surface, the full surface you embedded the pair of pans in, such that K is less than this map HPIJ that you get from this gluing process. And then for all possible seminorms on the glued surface, because the K is this here's the glued surface, so the surface you start with and embed the pair of pans in, there should exist an SK bigger than this DK. Remember, this DK was the exponent on the growth on the sets, and functorial constants that depend on IJK on the surface, which is bigger than 0, such that if P shares two boundary components with sigma, so that's a B case, and the minus boundary P is B in this notation here, then for all vectors in the prime space of the complement, mapping class group invariant part of the complement, you need to have that when you glue a B onto that V and take the case seminorm, look at the case guy in the directed set and take the alphas guy in the set that indexes seminorms and compute this seminorm. This should be less than this constant times this funny norm, remember the supremum of all seminorms for the J of that vector times, and then 1 plus, and then the positive part of however much the length of the interior boundary of the pair of pans is longer than the exterior part of the length, to minus SK. Minus SK. So when this goes up, 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 this starts decaying. So therefore you see that, you get smaller and smaller terms. The longer the curve, the longer you embed a pair of pans into the surface, wraps around, becomes very, very long in length. Then this has to decay.
Sorry, what is decay?
I go back and show you. There is decay. It's the growth of this set here.
Okay.
Yeah. So it has to beat that growth. That's the point. Okay. So you see the estimate here says that you take an SK that is bigger than the growth, and then this decay is faster than the growth, and therefore that wins. Okay. Sorry?
Theta was
Theta is the gluing morphism. It's the one that says take the vector space for pair pans, take the vector space for the complement, and do a bilinear mapping with the vector space. Okay, so that is precisely the definition. This is admissible initial data, and I gave a precise definition before, and the theorem says then the recursion runs, and you always get that omega sigma lies in the prime space. And all the series that defines it are absolutely convergent. And because they're absolutely convergent, they will be mapping class group invariant, because when you have a sum that's absolutely convergent, it is invariant under changing the order of the terms in the sum. And that's why it's mapping class group invariant. Because all that mapping class group is doing is just permuting the precisely, right? Okay. And so here's the basic idea behind the proof. So you start by using the decay action. And so you're saying that for all s bigger than 0, what you do is you take I for the pair of pans, J for the complement, K for the glued surface, grab a semi-norm for the kth guy on the glued surface, look at this absolutely series of the sum for the norms. Then by this decay action, which I just showed you, here's the estimate, except that it has this factor here. But all that I used was this estimate here, where I got this thing here for each of the term in the pair, in the sum over pair of pans, and then I simply just define this zeta function here to be that guy here. And then the point is simply that if sk is bigger than dk, well then this decays faster than the cardinality decays when I do truncate according to length of the sum here. So therefore this is a nice well-defined function. In fact, it's analytic in sk when sk is bigger than this. So that's finite. So in other words, I get this finite thing here, so I see immediately that these guys here are actually absolutely convergent. But now I need to work a little bit harder to actually get the estimate so that I know it ends up in E prime. So then that's where I use Well, I already used the small pair of pants axiom because the small pair of pants axiom just said, you see, if I have a small pair of pants, this will return 0. So if I have too many small pair of pants, infinitely many small pair of pants, this will diverge because it gives 1 for each small pair of pants. So if I only have finitely many small pair of pants, I can ignore those when I'm doing analysis. Okay, and now what I say here is that the lower bound action, so this epsilon lower bound, it says that that there is some constant here that gives a uniform upper bound on all of these zeta function evaluations for alpha in here, over all the seminorms. And so therefore I can actually say a better estimate for this is actually this thing here, where you see I have eliminated the alpha dependence. So now it's uniformly bounded in alpha. And that's what I need. And so therefore I know this is absolutely convergent, and it actually lies in the E prime sets.
So this is the B part of your definition.
That's the B part of my definition. Then you run the same page for C. There's virtually just replace B for C, and you have the proof for C with a slight modification because the axiom is not exactly the same. But I mean, it's almost the same. Yeah. So that's trivial.
I trust you.
That's trivial. That's true. So yeah. Okay. So that's actually proof why it works.
Right.
Okay. So just a few comments about topological recursion, geometric recursion revelations. So topological recursion was invented by Chekhov, Ellegaard, Orantin around 2005 to 7. It was made precise and written down by Ellegaard and Orantin. As you have seen in lectures here, it takes as input a spectral curve together with a 1 form and a 2 form on a twofold product of the spectral curve. It produces forms that are indexed by non-negative integers g and n on products of spectral curves. So on n-fold products of the spectral curve is where omega gn lives. They're defined recursively by a scheme that's reminiscent of, the irreducible components of the boundary divisor of mgn bar. Should have been there. So in parallel, after this event here, in 16 to 17, Kontsevich and Seubermann invented quantum structures. It takes as input these A, B, C, D tensors, which is, the data they need to define and quantize a quadratic Lagrangian. Maxime talked a little bit about it. He talked a lot about it last week, and a little bit about it now this time here. And then for any initial data, one can construct, for TR, one can construct these ABCDs and get a quantum area structure. And the output of TR is actually now encoded in Kontsevich and Seubermann's general construction of the quantization of this quadratic Lagrangian. And so the geometric recursion is something that I did together with Gaëtan Borot and Nicolas Orantin. And we started, so it's basically invented in this period here. Our first version of this used the spectral curve technology, but then when we saw the ABCD formalism in Kontsevich and Seubermann, we thought, oh, that's very, very smart that we can really use that and somehow categorify that and put it into a setting here. So we did that. But notice that TR is rather different from topological recursion because it is a functorial assignment. It has these actions of mapping class groups and so on. So that's what makes it different. And it is manifest that G means the genus of a surface and N means the number of boundary components of the surface. And then I will show you that there is actually a very nice relation between GR and TR for the target theory Teichmüller space.
So the mapping class group it acts, but not invariantly on the topological recursion.
There is no action of the mapping class group at all. Of these surfaces. They are numbers, right? Omega gn are forms.
But the data of the spectral surface, I could act on that, right?
That's a completely different surface. That's the thing. That surface is nothing to do with all of these surfaces here. And that surface, the G and the N in topological recursion has nothing to do with G and N of the spectral curve.
Right.
Because for all G and N you get omega GNs for a given spectral curve. And that's a bit the same here. For any theory here, you get assignments for all G and N. For all surfaces for all G and N.
And maybe you'll talk about this later, but may I ask, quantum area structure is a very important condition for the total symmetry.
Yes, so I will not talk about this, and what you see is that I have given you no relations that ABCD has to satisfy, but I have also not released the fact that one boundary is in and the rest is out. So I'm not claiming the symmetry under that. But we have, if you look in the paper, there are relations that one can impose on the ABCD in such a way that the whole thing becomes invariant under the entire mapping class group, permuting all boundary components as you like. Okay. All right. Yeah. So this has gone way too slow. I of course made the huge mistake of doing this analysis in detail for you. So I shouldn't have done that. But anyway, let's speed up now, okay? So I'm going to take a surface and I'm going to mark points on its boundary. Then I look at Teichmüller space. And that Teichmüller space is simply all diffeomorphisms from sigma to S, where S is a bordered Riemann surface. And such two are equivalent if and only if there exists a biholomorphism from S1 to S2 in such a way that the composite around here restricts the identity on the marked points, and its isotopic to the identity via diffeomorphisms also restricts the identity there. That means that there is a projection from that Teichmüller space to the Teichmüller space I started talking about in the beginning. And this is actually an R to the number of boundary components fiber bundle over this. If I now take the subgroup of the mapping class group, which are generated by Dehn-Twist that are parallel to the boundary, then I can factor that out of this space here. And now I get the quotient I call this, and that's now a U1 bundle over that guy. Okay. So I think I maybe also, well, no, this is wrong, because now I gave you all the details of the target theory. So I should tell you precisely what is it in Teichmüller theory. So here it is, and that's what I've been alluding to all the time. You define the systel set K sigma epsilon for any positive real epsilon. And you define E epsilon to be continuous function on that subspace, or that subset, open subset. Sorry, I made it bigger than equal, so that closed subset of Teichmüller space. And so then I have, of course, a family of semi-norms for each epsilon, which just consist of all the compact subsets of that set, and you take supremum norm of the function on that compact subset. So for continuous functions, this will give you such a space, so a complete Hausdorff locally convex topological vector space structure. And what we see is that when epsilon is smaller than epsilon prime, I have linear restriction maps from E epsilon to E epsilon prime. Very good. And so therefore, if I define E here to be continuous function all over, that's actually projective limit over R plus of the system. And now I see that the semi-norms, which are the supremum over all the compacts, is exactly the supremum norm for the systel set. E prime here is simply saying that things are in E prime if they are universally bounded on all the systel sets. But that function can still blow up on Teichmüller space, even though it's bounded, of course, on all systel sets, right? If you look at the quotient down in moduli space, then systel sets are compact subsets of the moduli space, right? And their union is all a moduli space. So they exhaust the moduli space curves. Okay, and now I define these length functions. And actually, we do it in terms of minimum of the length over the compact subset. So here you see if I have an epsilon and I have a compact subset inside that epsilon k, then I define my semi-norm now indexed by those two things as the minimum of the lengths of the curve with respect to points in that compact subset. And then there's actually some theorem that tells you that if you take one point in that compact subset, then there is a constant strictly in between 0 and 1 such that this here holds. So you get a lower bound, and there's another constant that also gives you an upper bound, actually. And this has to do with, quasi-conformal maps and how much they distort length and so on. It's a classical subject in the Teichmüller theory. And so this here allows you actually to deduce the lower bound axiom, and then the result of Ravine, which was defined by Miyazakani, guarantees that you get the polynomial growth axiom. And then there's work by Hugo Parlet that actually shows that the small pair pants axiom is satisfied. So Teichmüller theory defined this way here gives us a perfect target theory for the situation. And so now let's look at the small things that we need. So for a pair of pants, what's the Teichmüller space? Well, the usual Teichmüller space is just R plus to the 3 lengths of the geodesics of the boundaries, right? But in this version I'm working with, when you're looking at the initial one that I defined just before, it's R plus cross R because there's a twist parameter at each of the boundaries. And then if I divide by the boundary parallel Dehn twist, I get this space. And so the coordinates on the space here I call Li theta I by the analog with French-Nielsen coordinates. Okie dokie. And so now what I want to do is show you the gluing maps. So I have to do disjoint morphisms and I have to do the gluing morphisms. And I need to discuss a little bit of topology before I do that. So if I take two objects, sigma 1 and sigma 2, and I want to glue them along some matching pairs of boundaries, okay, then of course I can only glue, if I take an arbitrary point in Teichmüller space of the disjoint union, it won't work because if the lengths of the geodesics don't match that I want to glue on, I can't glue and get a hyperbolic surface. But if they do match, I can glue. And I get a complete, I get a hyperbolic metric on the complement, on the glued thing. So therefore, I define the subvariety of Teichmüller space of the disjoint union where the lengths I want to, of the boundaries components, pairs that I want to glue on, match. That's what this means. And so I glue and I map to the Teichmüller space of the glued surface. What can happen is that you see, what are the fibers of this map here? Okay? And so the fibers are, remember that I'm allowing these twist parameters now. So I can twist, okay? But if I twist the same amount on each side, then after I glue, this mark point is gone on this curve. So I can let it undo and go back. So therefore, there is a fiber of this map here. And when I divide by Dehn twists, which sort of twist this way on that side and this way on that side, that doesn't do anything because that can be undone after I have glued. But the point is that when I do this division, this here is a U1 to the number of pairs fiber bundle over that. So that's the structure I need to do, or to understand, in order to understand the following thing. First of all, the union morphism. So that is something that goes from there to there, right? And in this case, it's totally simple. Teichmüller space of the disjoint union is just the cross product of the two Teichmüller spaces. And so I have a projection onto two factors. And so I just take two functions, pull them back to this cross product and multiply them. That's the disjoint union morphism. Simple. The gluing morphism is almost as simple, but that's where I needed this fiber bundle from before. Because what I do now is I first take the disjoint union of the two F's. That lives on Teichmüller space of the disjoint union. Now I restrict it to the subset where the lengths of the boundaries I want to glue on agree. That forms a U1 bundle to the number of pairs over the space that I want to end in, namely the glued surface. So I just integrate along the fibers. And I do so with respect to a rotationally invariant measure on the fibers. Perfect. That's what I need. That's all I need. Now I have Teichmüller theory ready as a target theory. So now I just have to specify initial data. What is initial data? Well, A and C, there are no analytic conditions on, right? But they have to be invariant under the mapping class group, so that turns out to best be continuous functions on R plus cross U1 to the third power S2 invariant, where S2 flips the two last pairs. Perfect. B's, totally arbitrary continuous functions in those spaces, but they have to be related. If I take and flip, I get from one to the other. D, arbitrary as long as it's mapping class group invariant. And then here is what it means for those B and C to be admissible. They have to satisfy this condition here. And so I'm just spelling out the condition you've seen before in this specific case. Good. So you can run it. Whenever you have initial data satisfy this, you can run it. It will give you invariant functions on Teichmüller space. And so here's the most beautiful example, I think, of all of this. Take these functions here. So take A to be 1, take B to be that, take C to be this, and take D to be the sum over all ways of cutting a one-hole torus into a pair of pants, and just evaluate the lengths like this. So the theorem then, of course, is, since we called it the Mirzakhani-McShane identity theorem or data, is because the Mirzakhani-McShane identity allows you recursively to prove that this gives you the function 1. So how are we doing for time? Terribly. 6 minutes, 5 minutes like that. Okay. So I should say a little bit about how this goes by shooting geodesics. I will drop that. It's very nice, actually. But so I just go on. You can tropicalize these. If you tropicalize these, you get what we call conserved initial data. They look like that. The reason why we call them conserved initial data is because what do they compute? Well, they give functions on moduli spaces, as always, because geometric recursion always gives functions on moduli spaces if you start with target theory, Teichmüller theory. And so, if you take those functions and multiply them onto the Liouville volume form and integrate, you can actually express this in terms of these pairings of psi classes on MGN bar. And so this formula here actually allows us to somehow, I mean, this is why, I mean, this expression here is the one that Conservist worked on. Yeah. We can do these sums over multicurves. I just defined the function this way here. I told you about this function in the beginning. And then what happens is that if you take the initial data of Miyazakani-McShane and you just F-twist them the following very nice way, this only involves the go into the growth, that they have to be independent of epsilon. And so if that is the case, then we know that the functions that result from GR are integrable over moduli space, and they satisfy this recursion. And this recursion is, again, just the Laplace transform of the TR.
But what is the spectral curve here?
So I didn't give a spectral curve here, but the ABCD is in terms of quantum area structure.
Right.
So this gives an instance of quantum area structures.
So spectral curve is equivalent to that?
Yeah, so what the precise statement is there, I'm not quite sure. So what I know is quantum area is more general than topological recursion,
Right.
but I don't think that anybody knows how to construct the spectral curve from a given instance of ABCD for quantum area structure.
But there must be some categorical way of doing that?
Probably. I just don't know how to do it.
Okay.
I mean, maybe from what Max explained, it's doable. So So I have now discussed this so much with Max and Jan that they can't hear this lecture one more time. I fully understand. Okay. So there is a way to, what should we do? What should we do? I go 1 minute all because you took 1 minute to explain your thing. I skipped entirely this closed string field theory. It's very nice though, but let's forget it. And this is also very nice, but I forget that too. I just want to emphasize that there are 3 more lectures coming up on this very soon at this conference. But what I want to actually just quickly show you via pictures is that this here is what I was really hoping to tell you about this on top also. And so this is this function that comes from the Laplacian, right? And actually, so the thing is that what you should do is you should consider surfaces with corners, and then you don't recurse in the Euler characteristic, but you recurse in 3 times the Euler characteristic minus the number of corners. And then you require that to be less than or equal to 0. Because then you start with a surface which has that number equal to 0, and that's a triangle.
But corners, you mean just angle P or what? Or
Angle
just-
P.
I mean, it's orbital point of order 2.
No, they can have any angle you want.
Okay.
Okay. So you take corners with any angle you want, but you always talk about hyperbolic geometry, but I don't. I talk about smooth surfaces, so the angles have no angle. There's just corners on a manifold, right? With corners. Okay. But the thing is, you can run exactly the same. And now there are, boundary triangles, boundary interior triangles, and interior triangles. So in my talk last week, I did this, carefully, and I was sort of showing you the example where I didn't include these. That's possible. You can always put these equal to 0 if you want. But let me give you the full one. And so then there is this cylinder embedding here. So there are 3 ways of embedding the triangle, and then there's 1 way to embed the cylinder like this. And I want exactly a recursion that involves those. And so there is a completely similar statement with certain decay properties. This works. It's just the same thing. And then I want to show you a very nice little thing. If you start with a triangle, here's the Teichmüller space of the triangle. Here's the Teichmüller space of the cylinder with 1 point here at the boundary. So you can't have hyperbolic structures on this guy because there is a cone point here. And so if you take the following initial data here, where I haven't specified what this f here is, and you run the recursion, in this case you get the function 1. So this is a new Mirzakhani Mac-Chain identity for surfaces with corners. And so now if you then do isotopic class an immersed curve on the surface, and you define the function this way. So now we are summing over all primitive geodesics on the surface in the hyperbolic case. Not simple. Primitive means that the geodesic runs once, but it can self-intersect now. And that's the big difference from before. I did simple closed curves before. Now I do immersed curves. But I run them only once. I don't run them twice or 3 times. And so when you do this here, you also get a continuous function on Teichmüller space, and this satisfies this recursion here. So you see it starts becoming more and more complicated, but it's still very nice combinatorial stuff. And then the thing is that once you can do that, you can do this one by the Selberg trace formula.
Oh.
Yes.
And so this is the Selberg trace formula that re-expresses this in terms of sums over primitive geodesics. And so this means that you can now do a recursion for averages of these guys over modular space. And that's important because that tells you that you can actually get statistics of eigenvalues of the Laplacian. And so that's been a long-standing problem in analysis, is to understand the such statistics of eigenvalues of the Laplacian grid. But this follows from this open geometric recursion, and then the same principle that if you integrate over moduli space, you get some kind of topological recursion-like thing. But now it's not the usual topological recursion, but it's one that involves triangles and cylinders.
Do you have something to say about the Selberg zeta function?
Yeah, the same, because it's the same thing. I mean, up to these sort of simple factors here, you see these two are the solutions of geodesics.
Right.
This here is just some boundary contribution, that's explicit. This G here is actually just the Fourier transform at 0 of f, and this is an explicit thing as well, right? So all you needed to understand is those two. and that's understood by this theorem here.
You get any?
So therefore you can say things about statistics of eigenvalues.
Right.
And you can say what the averages are. Yeah, we get a formula for what the averages are.
You have new identities that are related to the Silberg trace formula that arise from this.
This is brand new, so I don't know. I mean, we should write everything out in detail and
Yeah,
to
right.
understand what happens. But yeah, I think this is a big problem solved.
And what about Bayes' explicit formula? We want to say that. So find that in your technology.
Excuse me, maybe
I don't
you maybe we move to questions.
Yeah, I think we're already doing that.
So, are you at your conclusion then?
Yes, this is the
Okay.
conclusion.
Okay, so first we should thank Jørgen again.